Hey, welcome back to the Lab 13, Interference and Diffraction. This is the second experiment that you're going to be doing, and it is the pattern that's formed when light goes through a single slit. They call it a diffraction pattern, and there's interference involved, but they call it a diffraction pattern because the light, as it goes through an opening or passes by an edge or whatever, bends around it. And when there's bending that goes around, and the light moves away from after bending, it can create interference. So we're going to let light go through a little opening. And for instance, up here on the screen, this opening here is about the size of a wavelength of the light. And when that happens, the wave came in as a plane wave, will go out as a spherical wave. If you open that opening up a little bit, by the way, the opening is labeled A. When we did the double slit, the distance between the opening is D. But the actual opening itself is A. And so if I make A about 10 times bigger, then you get this kind of pattern right here. And it turns out that the spherical shape on the edges of the wave will actually cause the wave to interfere with itself. And that was discovered after Young had done the double slit experiment. Somebody said, well, wow, this is pretty weird. What if we just let light go through a single slit? And lo and behold, they discovered the interference effect of light bending around and then interfering with itself. And lastly, this is, this opening here is about 15, 16 wavelengths. And you can see most of the light going through is nice and flat, and it's just on the edges that it's spherical. So somewhere between wide opening and closed up so it's the size of a wavelength is where we see diffraction well pronounced. All right, now this picture right over here is light that's passing over the edge of a dark opaque object. That means light's not going through it. And when light goes over that edge, it'll actually bend and then create an interference pattern that looks like that, which is insane. It's just amazing the type of patterns that light makes when it goes through things or over things and bends around it and creates an interference pattern on the wall. All right, so we're not going to be looking at this more complicated case. We're going to be looking at light going through a single slit, like this one right here. All right, now here's a picture of light going through a single slit. And this is done with water. Okay, so this is a water photograph. So you can look down on it, see the crests and troughs. And if you go straight away, you can see it's nice and bright on the screen at the central line. And so this is an intensity pattern over here to show you how bright the center is in relation to the next bright spot, which is right over here, and then the next one's over here, and the next one's over here. So the intensity pattern falls off rapidly from the very center. And you could see that when I shined the light through the diffraction gratings before. The central spot on the wall was like super bright, and then it got radically dimmer, and then dimmer and dimmer and dimmer and dimmer. So you see the same pattern whether it goes through one slit or many slits. Okay. Now, the geometry for it looks a lot like the geometry before, but when it comes to diffraction, it's easier to come up with a formula that predicts where the dark places are. And so if you look over here, that's going to be right here, and then it's going to be here. The person who drew this is a little bit off in their drawing, but anyway, there's the next one right up here, and then so on. And we want to be able to describe the dark places, the place where the light from one bending interferes with the light on the other side. And that's when they're 1/2 a wavelength out of step. So remember, destructive interference occurs when the crest and the trough line up. When you get crest and trough, you get 0. All right. So anyway, we have to use a different way of describing it. What we say is, if we imagine the opening made up of a whole bunch of little point sources of light. And they're all producing spherical waves that are going out. Then we match up the first one with the middle one. And then the next one with the one after that. And the third one with the third one from the middle. And we work our way all the way across. So we imagine those two waves. This one, the first one here with the first one there, and then so on, producing an interference pattern like a double slit pattern, but this time they're producing total destructive interference. So when they hit the wall over here, at that spot right there, they're going to be a distance out of step, which is 1/2 of a wavelength, rather than a full wavelength. Now when you do the geometry over here, this is a 1/2 a wavelength over here. This whole distance here is A. Actually, I made a little mistake there. So if we go with this triangle right here, this is 1/2 a wavelength for here. For the whole triangle though, this would be a full wavelength. So we're using the same distance right here. So, but we're going across the whole thing. So like right here would be the triangle for a 1/2 a wave, and then the whole thing would be a triangle for a full wave. So this distance A would correspond to a full wavelength, and then you end up with getting the same formula again. Because, by the way, I have D up here. This should be an A. So A sine theta. Actually, I got the wrong formula up here completely. Let me put it up on the board. So what we have, we just cut the slit in half and look up. Let's see, I need a pen. Okay, here we go. So we got this whole slit, and it's open at distance A, and we're going to cut it in half right here, and then this would be A over 2. Okay? We go to the screen, and those two spots over there on the screen are going to totally destructively interfere. That means that this distance across right here would be 1/2 a wavelength for m equals 1. And then the same thing down below. Now straight away, you got a nice bright spot in the middle. Okay? So if we do the geometry on that, then the hypotenuse is A over 2, and the other side is lambda over 2. And there's the angle right there, theta, and you get sine theta of m, the mth bright line, is equal to the opposite side of the triangle, 1/2 lambda, over A over 2. Well, you can see the halves cancel out, and you're left with just plain lambda over A. And if you put the A over on the other side, then we get the equation that A sine theta m is equal to m times A. And m is equal to 1, 2, 3, and so on. So for a single opening, we have to play a little game here that isn't as obvious as a double slit formula, where we break it up into two parts. So you can see over here the yellow triangle, and we just treat like half of it. So this over here, this distance right here, is going to be 1/2 of the A sine theta. Okay? And we get the same looking formula though. So the nice thing is we're dealing with what appears to be the exact. I forgot the lambda. I put A in there instead of lambda. So lambda goes right here. So that looks a lot like the double slit. D sine theta m equals m lambda. But remember, this is for an m is equal to 0, 1, 2, 3, dot, dot, dot. Remember, this one's for bright spots. And this is for dark spots. All right. So that's it. And again, in the lab, when you do the lab, you need to measure the distance from the opening to the wall where you're going to project the pattern, and you got to use tangent again. Tangent's equal to y over n, y of m, the nth bright spot, divided by L, and that'll give you the angle. Now you can do this at PHYT, the site you were at last week, for the single slit. It's very easy to do. They don't give you any ruler at the website, but it doesn't matter because you see all you need is the ratio of Y over L. And when you do that, it doesn't matter what unit you use. So we're going to actually do half the lab. You're going to do half the lab at the PHET site. And then we're going to give you the data for the double slit, because the double slit doesn't work out well at the PHET site. But the single slit works out great. So now what we're going to do is show you this setup. So Mr. Sylvester is going to take the camera out and come on over, and we'll show you how the whole setup is made. And then we're going to project the patterns over on the wall, that big cement pillar that goes through the room here. We're going to project it right on the wall here. So what we have is, we have two lasers. One is red and one is green. The green laser is set up right now. It snaps right into the optics table like that. All right? It's got two little screws in the back, so you can adjust the screws so you get the maximum light through the openings. Now the openings are on this little dial right here. So for instance, this little unhappy face right here is two slits that vary in distance. So it's a variable double slit. So if you're actually doing that in our lab, you would actually get like 5 measurements from that variable double slit. And then you can go over here, and there's a double slit here and a double slit over here. And you project it up on the wall, and then you can make your measurements from where this is called, by the way, this is called a high precision diffraction slit. And it's got multiple slits. This one is a high precision diffraction slit, and it just has single slits. All right. So I'm going to show you the single slits first, since I have it all set up. So I'm going to turn the laser on. All right. And you can see it's very, very hard to see the light over on the wall. So I'm going to turn the lights out. Got to work in the dark for this kind of experiment. All right. And if you get up a little bit, can you get up a little bit closer?
Yep.
Okay. Now, you can see right here, this is the central part. All right. The very center of the diffraction pattern. This is m equals 1, m equals 2, m equals 3, m equals 4, and so on. So what you need to measure when you do the lab is you measure from the dark spot on one side to the dark spot on the other side and divide by 2. And that'll give you y1. Now we're not going to do y2, y3, y4. We're just going to look at m equals 1. So you'd measure that distance where it's dark over to the other dark side and then divide by 2. And L is the distance all the way over to the table over there. So to see this type of pattern, you really have to get far away. So what we would do in our normal lab is you'd point it towards the wall. And it turns out it works perfectly when you do that. Now what I'm going to do is it's a variable slit. So I'm going to change the variable slit and you can see what's going to happen. Right now it's set for the smallest opening. So I'm going to make the opening bigger and bigger. All right, actually, this is the smallest opening right there. So you can see it's really spread out. And then I get closer and closer and closer. The opening's getting bigger and bigger. Ooh, I'm losing it. Getting bigger and bigger. I'm at the end of the track, right there. That's the biggest opening right there. So again, you'd measure from there, that dark spot to that dark spot, and then divide by 2. And by using the variable slit, you can get 8 measurements. There's also like 4. There's 4 of the 8. There's just like single slit openings you can send light through. But the variable one will fill in all the extra. All right, so now I'm going to put the double slit in there and show you the exact same thing. And if you use a different laser light, it will show up on the wall at slightly different distances because green has a shorter wavelength than red. Okay, so this is a double slit pattern, and when the D is really, really small, really, really small, So the distance between them is really small. Now, this is, I'm sorry, that one right there. So you can see how many there are. There's a ton of them. This needs to be adjusted a little bit, but you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So when I got the thing the furthest apart, so D was as big as you can, actually this is D is as big as you can get. Now this is the first diffraction minimum over here. So you see the opening size of the slits is creating that dark line right there. All of these spots right here are double slit interference. So the very center one would be M equals 0, and then you move over 1, 2, 3, 4, 5, and then the other direction 1, 2, 3, 4, 5. I'll try to adjust it a little bit so it looks like a little bit cleaner. Actually, when you look at it from back here, it looks better from back here. All right, and there's that little adjustment screw. They make it a little bit easier to see the spots. Now I'm going to make the slits further apart. Now when I do that, now you got to get really close. You can't believe how many constructive maxima there are. All right, so you go from one end to the other. You can just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16, 17, 18, 19, 20, 21, 22. What you can do is you can measure like 23 of them. 23 of them. And the odd one, the 23rd one, is the 0 in the middle. So you measure that distance and then divide by 22. 22. Because the one in the middle is 0. It doesn't count. And then that will give you the distance. That will give you the distance from one bright spot to the next. Look how tiny that is. So that's why you have to get so far away. And then you know your L value, the distance from the laser to the wall, and then you measure that distance, like 23 of them, and then divide by 22, and then you'll end up with the distance between two of them. And the angle is so small that they're equally spaced. So as long as the angle is below 15 degrees, they're equally spaced. And this is well below 15 degrees. Okay? So it's a very tiny, because the setup is way across the room. It's almost halfway across the room. All right, and that's a double slit experiment. And then you have to measure those angles for each of the opening, the distance between the two openings. All right, I'm going to turn the lights on. That's going to be about it. Okay, so once again, here's a laser right here and the double slit. I'll put on one of those double slits all by themselves. And let's see what we can get. It's the wrong way. Over here, hang on 1 second. All right, so I cut in half. Let me turn the light off. And can you see that with the camera?
Yeah, I can see it, but the resolution isn't very well.
But when they're close together, you get very distinct maximum. And when they're far apart, then you get a ton of them. You can still see the individual ones, but you got to get right up to the pattern to be able to see it. All right. If I put red on there, red will blow it up a little bit bigger. And that's the red one. So you can see that it's a little bit bigger pattern. We had the same setting before with the green. They're much closer together, and this is with red. Okay? So that is a double slit pattern, and we're going to give you the data for that. And for that experiment, we have 6 gratings, so you have to make 3 measurements off of the double slit. So you're looking at the original Young experiment where he sent light through 2 slits that are really far apart. And you can see, you can just barely make out the interference properties of light on the wall there. So he had to project that thing way across the room to see those fringes that he was talking about. But anyway, that's Physics 2 lab, and it's been a pleasure being your instructor, and I'm going to miss you. I miss you already because you don't come to class anymore. But anyway, we'll meet up again in the fall and have our welcomes again. But anyway, it's been a great pleasure, and I wish you the very best on the final exam. And you're going to be working with your group on the final, so that'll be nice. Anything you'd like to add, Mr. Sylvester?
No, God bless and stay healthy.
Definitely. Take good care, and we'll see you later.